So the problem states that the rails in the figure below each have a resistance of 2.2 ohm per meter. The bar moves to the right at a constant speed of 9 meter per second in a uniform magnetic field of 0.8 Tesla. Find I as a function of t when t is greater than 0 but less than 1 if the bar is at x is equivalent to 2 meters at time is equivalent to 0 and a 0.3 ohm resistor is present across the left end with the right end open circuited. So based from the problem, we have the following given. You have the resistance of the rails, which is 2.2 ohms per meter. So 2.2 ohms per meter. You have you have the velocity, which is 9 meter per second, moving to the right. And you have the magnetic field, which is 0.8 Tesla. And lastly, you have a resistor at the left end, so somewhere here, whose value is 0.3 ohms. And the right end is open circuited. So in order to solve this problem, we need to apply the concepts of Faraday's law. So in order to find the value of I of t, so we know that I of t based from the Ohm's law is equivalent to the voltage divided by the resistance. So we need to find the voltage, which is also your EMF, and we also need to find the function of our resistance based from this problem. So let us first find the function of your EMF. So based from our Faraday's law, your EMF is simply equivalent to the negative derivative of the flux with respect to time. Therefore, we need to find the function of the electric flux. Now, in order to solve this problem, we know that your electric flux is simply equivalent to the magnetic field B multiplied by the area where the object is moving. So the magnetic flux, the magnetic field is constant, which is 0.8 Tesla, multiplied by the area. So the area is this is simply a rectangular form, or the surface area is rectangular. So you have length multiplied by the width. So we have 0.2 for the width multiplied by the position of this bar. So as you can see, this is continuously moving at a rate of 9 meter per second. So as time moves forward, the length changes from 2 plus 9t. So it started from x is equivalent to 2, so maybe somewhere here, let's say here. And then, as time moves forward, it increases by 9 multiplied by time. Okay? So, therefore, we now have the flux, which is equivalent to 0.8 multiplied by 0.2. So, let's use your calculator in order to solve this, in order to simplify this problem. So, we have 0.8 times 0.2 multiplied by 2. So you have 0.32 plus, we have 0.8 plus 0.2 times 0.2 times 9t. So we have 1.44t. So plus 1.44t. We now have this value. We can now solve for our EMF by using the derivative. So the EMF is simply equivalent to the negative derivative of the flux with respect to time. So 0.32 plus 1.44t. Okay? So the derivative of a constant is of course 0. And then the derivative of 1.44t is 1.44 multiplied by the negative sign. So we have minus 1.44. Therefore, the EMF is simply equivalent to 1.44 volts. We now have the EMF. Let us now calculate for the resistance. Now, please take note that in this instant, when the bar is in motion, the resistance is also increasing with time. So, the resistance of the constant resistance on the left end and the moving resistance on the rails. So, we can simply have that the resistance is changing with respect to time. So, we have the constant resistance, which is 0.3. And since this is simply in series, we have plus 2. And this is a resistance with respect to the length. So 2 because you have 2 rails multiplied by the value of the resistance per unit length. So 2.2 ohms per meter. And the length is changing again with respect to time by this factor, which is 2 plus 90. So you have 2 plus 90. Okay, so therefore, our resistance is simply equivalent to 0.3 plus 4.4 multiplied by 2 plus 90. So we can further simplify. So we have R is equivalent to 0.3 plus 8.8 plus 4.4 times 9. So we have 4.4 times 90. So we have 39.60. 39.60. So we can simplify this one in order for us to have the final answer, the final function of the resistance, which is 0.3 plus 8.8, and that is equivalent to 9.1. So you have 9.1 plus 39.60. So we now have the value of the resistance and the EMF. We can now simply substitute to find the function of I of t. So again, I of t is simply equivalent to your EMF divided by your resistance. So EMF is equivalent to negative 1.44 volts divided by the resistance, which is 9.1 plus 39.6 T. Okay, and since this is a current, you have the unit of uh, volts, of amperes. So the unit of this one is amperes. So if you want to find out the value of the current at a certain instant of time, you can simply substitute the value of t to the given equation. And that's it for our first problem.